Okay, so clearly this course is probability and statistics, and the first four chapters talks about the statistics part, and then starting in chapter five, we move on to the probability section before coming back to statistics later on in the course. Um, you've dealt with probability before. Um, from my experience, students like the probability section because they can compute that a little bit more readily easier and find the examples a little bit more related to something that you can deal with in everyday life. So I'm going to combine 5.1 and 5.2 together. Okay, so we'll go over some basic probability rules. We're going to kind of skip objective number 4, using simulation to obtain data. If you take a probability statistics course after high school, you'll be dealing with this, not necessary for this particular course. So what is probability? It's a measure of the likelihood of a random phenomenon or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. Okay. Now it says use a probability applet to simulate flipping a coin 100 times. Plot the proportion of heads against the number of flips. Repeat the simulation. Like I said, we're not going to talk about using the software for this, but if you just actually physically flip the coin 100 times and you record your outcomes, you should see something should occur very close to 100. Probability deals with the experiments that yield a random short-term results or outcomes yet reveal long-term predictability. The law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. Let's talk about flipping that coin. Clearly, there's only a heads or tails, which is 50%. If you flip it 20 times, you may not get 10 heads and 10 tails. But the law of large numbers says if you flip this thing, say, 1 million times, the chances of you getting closer to 50%, 500,000 heads and 500,000 tails, gets closer to that probability of the outcome. An experiment is any process that can be repeated in which the results are uncertain. So we flip a coin the first time. I don't know what happens the second time. It's just they're independent of each other. The sample space of a probability is the collection of all possible outcomes. And you can read on. So let's take our first example. Let's consider the probability experiment of having 2 children. That's the experiment. A. Identify the outcomes of the probability experiment. Well, you could have boy then a boy then a girl then a boy, and then a girl and a girl. Determine the sample space. Well, you could see how it's in set notation. We have the little braces here on the beginning and the end, and then parentheses. It's almost like a coordinate, right? You have an X and a Y. In this case, we have the sample space. We have a boy then boy, boy, girl, just like we have it above, separated by parentheses. C. Define the event E of having one boy. Well, that could be a boy then a girl, or a girl then a boy. Notice we didn't say boy, boy, because that would be 2, or 2 girls, that would be no girls. No boys, excuse me. The rules. Major rules of probability, and this goes from this section 5 all the way to number 8. The probability must be greater than or equal to 0 and less than 1. That is very, very key. The sum of all probabilities is 1. Very important. You cannot add probabilities and get something greater than 1. Very, very important. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2. And like I said, this is very, very important going forward. Here we go. We got some M&Ms. The colors can be brown, yellow, red, blue, orange, or green. If you randomly select from a bag, this table shows each color and the probability of drawing that color. And notice, if you add these up, this better be 1. An event that is impossible, the probability of the event is 0. So go back to the M&M. What's the probability that I get a pink M&M? Well, clearly that would be 0. If an event is certainty, the probability of getting 1. Excuse me. So what's the probability that it's a peanut M&M? Well, that would be 1 because they're all peanut M&Ms. An unusual event is an event that has a low probability of occurring, but it's not necessarily impossible. Okay. Empirical method. We're going to talk about classical and empirical. Empirical talks about the number of times an event is observed divided by the number of repetitions of the experiment. So that's just your basic division. So the number of times you pick a green M&Ms over the number of times you actually try this. So if you got 3 M&Ms out of 10, it would be obviously 0.3. If you flipped a coin 10 times and you got 2 heads, well, then it would be 2 out of 10, which is 0.5. 0.2, excuse me. You can read how to build a probability model using the outcomes and actually divide the frequency over the total amount. Now, classical method. This is your basic flip a coin. 1/2 would be your probability, either heads or tails. Go into a bag of M&Ms with those colors. I think it was 5, right? Brown, green, orange, red, and blue. Each color equally would be 1/5. That's your basic classical method. Having a boy or a girl, 1/2, right? Either a boy or a girl. Each probability requires equally likely outcomes. And you can see an example here. We are going to skip objective 4, as I noted earlier. Okay, so subjective probabilities is an outcome that is probability obtained on the basis of personal judgment. If you're into sports and you say, oh, I think the Rockets are going to win. I think they have about an 80% chance of winning this game. Well, that's clearly subjective because you may think it's 80%. I may only think it's 30%. Clearly subjective. There's no probability model that backs that up. Horse racing. A lot of gambling deals with subjective probability. It's people's feelings about something. And that's your introduction to probability. Key there is the rules. Sum of probabilities is equal to 1. And classical and empirical methods. Okay, some basic rules. The addition rule for disjoint events and the complement rule. 2 events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events if they have no outcomes in common. If you haven't done Venn diagrams in algebra, these would be disjoint. They have nothing in common. This doesn't intersect this. If set E is the numbers 0, 1, and 2, set F is 8 and 9, there's nothing in common about those two numbers, those two sets, excuse me. So what do we do about their probabilities? We just add them. We just literally add the 2 probabilities, and still that can't be greater than 1. So I think you should take time and look at the example. And I'll do that. The general addition rule. Now let's say they're not disjoint. They have something in common. Well, you must take the intersection and subtract it because basically, if you do not do that, you're doubling up and your probability will be greater than 1. So let's give you an example. If you have a dice, you know a dice has the numbers 1 through 6 on it. If I say, what's the probability of getting a even number or the number 2? Well, an even number would be 1/2, right? 3 even numbers, 2, 4, 6. And, or a number 2, well, you're going to basically add the number 2 twice. So you would have to subtract those that are even and the number 2. So you cannot repeat probabilities, and that's why you subtract by those that have something in common. The complement talks about everything not in the set. So the complement of even numbers would be odd numbers. And we know the sum of all probabilities is 1, so it's 1 minus that probability will give you the complement. So if this set is E, the complement would be everything outside the circle, and that little superscript, remember subscript is below, superscript would be little c. Well, here's a perfect example. The probability that you do not own a dog. Well, either you own a dog or you don't. So to find the probability that you don't own a dog, if I knew the probability of having a dog was 0.316, 31.6%, well, if I subtract from 1, the probability of not owning a dog is 68%. So actually more people don't own dogs than own dogs. More examples. And we'll stop there and we'll continue on in the next screencast.